This is section 14.2, part E, and we're looking at example 9. I'm actually going to go at this example a little bit backward. We're going to look at a picture of this vector field, and we're going to predict for each of these paths whether we think the circulation ought to be positive, negative, or zero. And then we'll come back and actually do the calculations and see if we're right. So, notice that this is basically a radial vector field. It really is a radial vector field. XY is our typical radial vector field. By dividing by the square root of x squared plus y squared, I've just divided by the magnitude. So this is going to be a radial vector field where all the vectors have length 1. I've got a picture of that I printed from Maple over here. And we're going to draw each of these line segments on my picture and see what we can predict. So here we go. Notice in our radial vector field, everything's pointing out along the radius, like a sunburst from the center. And all of the vectors are the same length, namely a length of 1 in this vector field. I have, for part A, the line segment from 0, 0 to 1, 1. So 0, 0 to 1, 1. So this is A. If you take a look at that, if I'm moving from here to here, notice that this vector field is helping me perfectly. This vector field is moving me in exactly the direction I want to go. So I'm going to predict that I would get a positive circulation. Along that path. Not only a positive circulation, but a pretty large, comparatively anyway, large positive circulation. Part B asked us to go from 0, 1, so right here, to 1, 1, over here again. A little bit brighter here. So here we have B, and I want to go horizontally, not vertically. So the vector field's not helping me with that, although it's not really hurting. I want to go slightly to the right, and notice the vector field is helping me with that. The vector field does push slightly to the right. So I'm again expecting a positive circulation, but not as big of a positive circulation as I got here. I'm not getting as much help from the vector field as I move from start to finish on that path. All right, in part C, we wanted to go from 1, negative 1 down here to 1, 0 there. So, in part C, it looks to me like the vector field is actually working against me, not for me. I want to go vertical, but it's pushing me slightly down and to the right, and I don't want to move in either one of those directions. So I'm expecting a negative circulation for part C. And then finally in part D, I want to go from negative 1, 0 to positive 1, 0. All right, this one's perhaps the most complex in a way, because something different is happening on the left side of the path and the right side of the path. On the left side of the path, the vector field is working against me. I want to go this way, vector field's pushing me that way. But on the right side, I want to go this way, and that's exactly the way the vector field is trying to push me. So as much as it helps me here, it basically works against me there. I would expect those two sides to essentially have the net effect of canceling one another out. And I think for part D, I'm expecting an answer of 0. All right, let's see if we actually get that analytically. So here we go. For part A, the path goes from 0, 0 to 1, 1. So that path is just going to be y equals x. And that means that I can set up my r. If I let x be t, then y will also be t. The derivative, r prime, will be 1, 1. And for f, here's my x and y. So I get xy, tt, over the square root of t squared plus t squared, which is actually the square root of 2t squared. If I pull a t out, that would be t times the square root of 2. And there's something here that I need you to be really careful about. I pulled the t out of here as a positive t, even though really with the square root I have to worry about whether it's positive or negative, because in this picture, all values are positive. X and y are both positive for every point on that path, so I know I have positive t values and I didn't have to worry about it. What that does for me is means I can rewrite this as just 1 over the square root of 2 and 1 over the square root of 2. So that's kind of nice. All right, my integral for circulation goes from, let's see, t would be 0 to 1, just like x. And I take the dot product of the f with the r prime, which is just going to be the 1 over the square root of 2 plus another 1 over the square root of 2, or 2 over the square root of 2. And the value of that integral is about 1.414 square root of 2. All right, let's do B. In B, I've got the line segment from 0, 1 to 1, 1. So that's just going to be the horizontal line y equals 1, meaning if x is t, y is always 1. And r prime is, going to be 1, 0, not 0, 1. Derivatives there. So for f, again I have xy on top. So that's t1. And the denominator is the square root of x squared plus y squared, which would be t squared plus 1. So my circulation, x is t, and x is going from 0 to 1 again. I take f, dot product with r prime, and let's see, that's going to give me t over the square root of t squared plus 1, plus 1 times 0 is 0, so nothing for the second term. And once again, just a matter of going through and integrating that on the calculator if you want to. I got 0.414. So both A and B gave me positive values for my circulation, but for A, I got a bigger positive value than I did for B. Let's remind ourselves what that looked like. A was the path where the vector field helped us perfectly. Every single vector in that vector field was pointing me exactly the direction I wanted to go. That was the larger positive circulation. For B, I was still getting some help. The vector field was pushing me slightly to the right, so I had a positive circulation, but it didn't help as much, and so it was smaller. And that's exactly what we saw when we looked here at our calculations. All right, let's look at D and E, or C and D rather. For C, I'm looking at the line segment from 1, -1 to 1, 0. So this is the line x equals 1, the vertical line. So since x is always 1, I can't let x be t this time. X has to be 1. I'll let y be the t value. And the derivative would be 0, 1. For f, I've got the x and the y again, always defined by r. So xy, 1t, divided by the square root of x squared, which is 1, plus y squared, which is t squared. And so, when I go to write down my circulation, notice this time the y value is t, and the y's go from -1 to 0. F dot r prime and let's see, the dot product here would be 0 plus t over the square root of 1 plus t squared. And again, I just used a calculator to integrate that. And this time I got -0.414. If I check back with my picture, we did predict a negative value of the circulation. We were trying to go kind of against the grain here, against the vector field. And notice we got the exact same negative value as we got a positive value up here. And you can probably see why. The length of the path is 1 in both cases. And by the symmetry of the field, this is helping just as much as this is working against me. So hopefully those also make sense. All right, finally we're going to look at D, where we were predicting 0 for a circulation. With D, we wanted to go from -1, 0 to +1, 0. To parameterize that, I'm going to go ahead and, since this is really just the line y equals 0, it's the x-axis, I'll let x be t again, and y has to be 0. So r prime would be 1, 0. And f is going to be our xy, so t0, divided by the square root of x squared or t squared plus y squared or 0 squared. Now this is where you have to be really careful with this one. We get t0 over the square root of t squared. I'm not going to simply write that as t, however, and the reason for that is t is the x value, and some of the x's are negative and some of them are positive, so I have to be a little bit careful this time. Let me write that as the absolute value of t instead. The square root of t squared will always be positive, even when the original t value is negative. So that's why I threw the absolute values on there. Because of that, in order to correctly integrate, I'm going to have to integrate the left side and the right side separately, since the absolute value of t has different values depending on which side I'm at. So, from -1 to 0, the absolute value of t would actually be the opposite of t. T is negative, and to make it positive, I put the extra negative in front of it. So f here is actually just going to be -1, 0. That means to get my circulation, I'm going to integrate from -1 to 0, this f, dotted with the r prime, which was 1, 0, dt, which gives me -1 dt, right, plus the 0 for the second term, which ends up giving me -1. What about the other side? What about 0 to 1? Going back to f, it was t0 over the absolute value of t, but now that t's are already positive, the absolute value of t is just t. So now I get 1, 0. To do my circulation integral, I'm integrating from 0 to 1. This f, dotted with the r prime, which was 1, 0, dt. That's 1 plus 0, or 1 dt, which is just going to give me 1. And there it is. If I combine the -1 with the +1, I finally do get a 0 for an answer, just like we were expecting. All right, that brings me to the end of our discussion of circulation integrals. Unfortunately, we're not quite yet at the end of our discussion of these integrals of vector fields. We have one other type of integral that we'll work with in the next video.